Good morning, everyone. Yeah, it's a real pleasure to see new friends, old friends. I will tell you a bit what we did in terms of hardware, software co-design, in terms of SmartEdge, but also a bit broader, right? What we did in my lab, and most of this was led by Alberto, learner in my lab, who is a specialist in this topic. And those slides were also taken from Rana, a former PhD student, and Eduardo, who's been working with us in SmartEdge, doing some optimizations. Let me start with the lab, Exascale Info Lab. Some of you came already to visit us, right? Carrie was, where is Carrie? Carrie was with us last week, actually. So please come and visit. We are, you know, here in Switzerland. It's a very special part of Switzerland, Fribourg, because it's the Rösti-Graben for you German speakers, right? So it divides this Rösti-Graben, it's the Rösti barrier, which divides the French part, as you can infer, I'm from the French part, from the German part, right? So the University of Fribourg is a trilingual university. It's the only one in Switzerland. We mix happily German, French, English, and quite a bit of Italian, though my Italian is non-existent. This was my group when I had the ERC grant a few years ago. Now it's a bit smaller. That's our building, thanks to our sponsors. So what do we do in Fribourg in my group? We do data infrastructures, right? This is very broad, but basically we are building next-gen backend for next-gen applications, right? And we are dealing quite a bit with data integration, with time series, with hardware, software, co-design, or heterogeneous hardware, and also increasingly with AI, of course. So we're doing increasingly lots of transformer-based methods for all kinds of applications. Today I will tell you a bit about heterogeneous computing and how we should accelerate workloads with hardware. And why do we want to do that? Well, I think you all know why, right? It's because, you know, I bought this laptop last year. It's a somehow 2 gigahertz laptop. And I think 10, 12 years ago, I also bought a 2 gigahertz laptop, right? So in terms of clock size, clock speed, sorry, we are not seeing much increase, but actually that's what Peterson and Hensey said in their Turing Award lecture a few years ago. You know, we had this great curve of processor performance, not only in terms of you know, clock speed, but really like in terms of multi-core, Dennard scaling, Amdahl's law, and all of this is stagnating these days for you know, heat, energy, physical reasons, right? So basically, I grew up at a time where you just had to wait 18 months and a fantastic CPU would come out and it would solve half of your problems, right? So this is unfortunately not the case anymore. It's really getting flat in terms of you know, performance, performance per watt, performance per second. And one way of circumventing this is, of course, trying to do something else than CPU alone, right? So you all know the GPU story, which is the biggest story in terms of impact through training, inference of deep neural network. But there are way more opportunities in this realm. As an example, you know, the M1 or here M3 chip, right, that is inside this laptop. So what did Apple do? Basically, they bundled together on a chip a bunch of different systems with different functionalities, and they are all kind of specialized for some functionality, right? So on those M platforms, you have, of course, some CPUs and GPUs, but you also have some specialized engine for, like, you know, neural computing, for inference, for vision, for graphics. So those are increasingly, like, you know, very complex, basically, platforms. What we will talk about in this presentation is a bit different. We'll talk about the different computing units which you can have inside a computer or across a computer rack, right? Across basically a distributed system or rack system where you also have switches, right? You already know that we've been working quite a bit with programmable switches in this context. So basically, you know, that's a typical high-level view of some computing element. You have a CPU, you have the memory, but you can have, you know, some advanced network card. You can have some advanced SSDs or like hard disks. You can have some FPGAs to accelerate some of the workloads, some tensor processing units, GPUs. You can have all kinds of specialized hardware. And so that's basically what I will talk about today. I will tell you a bit about heterogeneous computing, the RDMA, which was kind of the first part of what we did in SmartEdge. Then I will tell you about some recent papers we had for accelerating all kinds of graph processing using P4. What Eduardo did recently, optimizing a bit those different queries. I will tell you a bit about CXL and our latest focus in terms of LiDAR and specialized CXL systems. Okay, so let's do it. What's the vision, if I summarize now? So you have those different elements, right? And many of those elements used to be passive in terms of computation. If you think about the memory, it's typically passive. You don't change anything directly on the memory system or on the SSD system. The switch was used in the past simply to forward packets, right? You wouldn't change much in terms of the content of the packet. Same for the NIC. The network card typically would do some buffering, right, and some optimization in terms of the transfers, but it would not directly compute. But all those elements are very powerful, actually, right? And they are getting more and more powerful. And they also offer different kinds of functionalities. So typically, I will talk quite a bit about the switch. The switch is very limited in what it can do, but it's also exceedingly good at this feed-forward processing kind of pipelines. And the entire architecture wastes tons of energy and cycles to simply move the data around those components. So we feel it's a big opportunity, actually, right? When you move something, when you have all those, those components working together, why don't you also take advantage of, while moving the data, you do as much processing as you can on each of those devices, such that you will accelerate basically the workloads. So that's what Alberto says. No I/O should go untapped, right? If you do an I/O and input-output, why don't you also try to do some computing typically based on it? Not only on the CPU, but on all those different computational platforms, which are getting, again, more and more powerful. So that's one example to give you as a start. That's something we did before SmartEdge, just to give you an idea, right? The first idea of what you could do. That's something we did with Intel and Stanford at the time. It's simply triaging, right? You know that the computers, the CPUs, the big database servers, they all love when things are nicely pipelined, and then you can use all the parallelisms inside the CPUs. So what we did, for example, here is when you have different clients issuing requests to a DB server, what you can do on the fly using a smart NIC is reshuffle a bit those requests, right? Because some requests go well one with each other, right? There is some affinity typically between the requests. Perhaps they touch the same part of the database, or they use operators that are compatible, or basically partitions, which are all meant to answer those different queries. So what we did is, instead of simply taking those different queries, forwarding them through a switch NIC and then attacking the DB server, we reshuffle all of this to have basically nice partitions with compatible batches. And like this, you gain, like at least 8x performance in terms of UDP if you do UDP, or 2x if you do RDMA. We will talk about RDMA in a minute, right? So just to give you a first idea, okay, very typical database setup, which has a NIC typically, which is not super well used, and without buying any more hardware, simply by basically, adapting the software to the kind of hardware and application you have, you can gain 8x performance. Right? So let's start with something a bit similar that we are leveraging in SmartEdge. It's RDMA. Some of you have already heard about it. It's basically RDMA with a declarative extension. So what do we want to do? We want to basically send data using a minimum of latency, but also a CPU. We don't want to tap too much into the CPU to do that because it can be, as you will see, very costly. So you all know RDMA, right? It stands for Remote Direct Memory Access. It's the protocol which is used by high-performance computing and increasingly in all kinds of setup. You have different flavors of RDMA. And basically, what does it do? You remember DMA, right, from your OS courses. So RDMA gives the network card direct access to the host memory. And why do you want to do that? You want to do that to basically free the CPU of doing all those nitty little details when you need to transfer data, right? So the idea is the CPU tells the card what to do, right, in terms of, oh, transfer this to that. And then the data fetching and the sending do not use the CPU at all, right? And the idea is to have a greater performance or less CPU usage. One of the big issues we have in all the data systems that we are building is that we deal very often with small bits and pieces of data, right? Because the data is fragmented, because the data is multidimensional, and you want to basically project on some of those dimensions in a database because you have columns or you have rows, and you want to select only some part of it, like some attributes, some values. So when you deal with data, small data pieces, the RDMA doesn't work, basically, right? The performance is killed. We will see exactly why. And what can you do, or what would a typical database system do in that sense? You would try to circumvent this by having a buffer, basically, right? You have a big buffer, and you will start to copy all the small pieces to this buffer, and then you will buffer with RDMA up directly. You will do the transmission. Why is this bad? Guess what? You lose memory bandwidth and you use CPU cycles because you have to use the CPU to create this buffer. We will see this in a moment. However, there is one big opportunity that we will tackle, that we will use, that we will exploit. Typically, the data we use in all our data-intensive systems, it's not randomly scattered, right? It's scattered through patterns. If you think in terms of vectors, in terms of tensors, in terms of columns or rows of databases, then there are patterns in what we want in those different elements. RDMA is not able to exploit the proximity sometimes you have in the different selections you want to have for the data, and the regularity, right? Again, if you select the first field in a row based store, then you will have a specific pattern in what you select. And we want to change this by extending a bit this RDMA using a declarative interface and basically using hardware acceleration to help us in that. So the idea is to have overall higher bandwidth, lower latency, and no CPU utilization. We did a bunch of experiments to show this in practice, and this was published in CIDR a couple of years ago, if you are interested. So basically, we tried, commercial systems and basically RDMA verbs to do some OLAP reshuffling, right? You have, like, in this case, it's a column store, right? So the data is organized as columns. You have kind of a selection, right, or reshuffle. And what you want to do is basically take those, so-called scatter-gather elements, which point to the different elements you want to transmit. and this is a work request, and basically you tell via RDMA, oh, I want to basically RDMA that kind of data, right, using those 3 values. And if you do this, right, in a typical RDMA system, and we really check this low level, you will get tons of very small DMAs, which will kill the performance, right? And again, what you can do in a typical database system is have a transmission buffer to alleviate this, right? So you can copy basically up the different elements in your transmission buffer, and then you can have a more compact, right, RDMA, where you say in your work request, oh, you simply have to transfer this, and bam, RDMA will transfer all the data. But again, this is bad, because first you waste memory bandwidth, and then the CPU will have to do a lot of work, right? So those are some small experiments we did on a 100 gigabit per second card. If you do 0 copy, basically with the small, you know, those small reshuffling in OLAP systems, you will get perhaps 50 gigabit per second. No, you will get way less, actually. You will get almost nothing in terms of bandwidth, and you will use quite a bit of CPU. And if you do this copy out database server approach, you will use all your CPU, basically, right, to transfer those small bits into the buffer. And then you will get a bit better performance, but still the performance will be very disappointing, right? On this 100 gigabit, you will get 20 gigabit. And, you know, there is no free lunch, right? You have this basically real trade-off between latency and the bytes you transfer per the DMA. And basically, if you want to optimize things, you have to know what you're doing, right? Either taking a trade-off in terms of, oh, you take relatively large chunks and you have a low latency, or you transfer bigger chunks, you will have a great throughput but a pretty high latency, right? So all of this to tell you that this RDMA for data-intensive systems, for many of the systems we deal with today, it's not fantastic, right? It's not fantastic. It was not meant to optimize for those complex data pattern exchanges. So to summarize, in terms of constraints and what annoyed us in RDMA. First, in terms of data description, the data has to be described in the same order as it appears in the packets. Remember those SGE, right? It was exactly SG 1, 2, 3, it was an order, which makes sense for networking people, right? Obviously, you want to describe the packet kind of byte by byte. Then the NIC, when it does the operations, it must follow those scatter-gather elements, sequences, and it will issue one DMA operation per SGE, right? That's the way it works. Even though you could be smarter and perhaps do things differently, merge things, and do one DMA operation for several SGEs potentially. So it cannot take advantage of adjacency. And finally, the NIC cannot transfer data that is not going on the wire, right? So basically, if you have a hole, you have to kind of remove this hole, take the other parts which are not in the hole and transmit that. And we will try to basically, with DRDMA, solve all of this, right? So with DRDMA, we will declare the data positions using some patterns, right? We will tell to the card, oh, we have this complex pattern, and please transmit the data following this pattern, right? So this is a declarative approach. This is what we do in all the database systems. It's very high-level programming, and usually humans like this, right, in terms of description. And usually this is very powerful as well, right, because depending on your language, you can declare all kinds of crazy patterns. The NIC, in our case, must not follow the sequence, but it will determine, through an optimization, the DMA schedule that is best and performant for what you want to transfer. It does not issue one DMA operation per scatter-gather element, but it will do as many DMAs it sees fit to do the job, like flexibly. And finally, it takes advantage of adjacency. It can combine different SGEs, and the NIC transfer data that is not going on the wire, right? So perhaps if you have a hole, you can transfer the whole thing and then remove simply the part that is to be missing in this data transfer. And so you understood we call it RDMA because there is this declarative kind of database view on what should be transferred. So how does it work? It's a strict extension of RDMA. If you used RDMA, you know that it works with a bunch of verbs. So what we did is a strict extension of RDMA, such that we are kind of backward compatible. We have one additional verb that we introduced, and we have a set of non-contiguous regions that can be described with data positions, right? So it's a bit as usual. You have kind of the database issuing non-continuous region for the work. It sets up the NIC, but then you have the NIC which will determine this DMA schedule. But again, it will not take every bit one after the other. We have a small optimizer which will try to find the most efficient DMA schedule given what the database tells you to transmit. And then it will execute the DMA schedule in a standard way, like RDMA would execute this, and packetize in the end the results. So what kind of declarative artifacts can we have? For example, in the paper we described strided regions, right, which are very, very useful for rows, for columns, for vectors. The idea is that you have a pretty generic language to describe basically gaps and exactly what you want in those 1D columns, right? So it's basically data layouts with gaps at regular intervals. So how can you do this? Well, we have basically a bunch of variables where you define, the width of what you want to transmit. Oh, of course, you define the base. Where should you start transmitting? And then you define the period, because those things are obviously periodic, right? The vectors will be all the same, so the columns will be kind of all the same in terms of the attributes. You describe the number of elements, and of course, you also describe the gaps in all of this. So here, typically, right, you have one example where you describe, there is some periodicity here, every 4 elements, and you have a gap every 4 starting at 2, right? So here, basically, you would transmit either 3/4 of this vector or 3 attributes of this column, and you would not transmit this, right? That's the idea. So that's the declarative part. That's how you will basically define all of this. And of course, you can combine those expressions into multiple strided regions. So basically, you can describe columnar transmissions for multiple hosts, right? So you can do this also in a distributed fashion. You can interleave with other regions. So this is a fairly powerful abstraction that you can use with your different kinds of data. And you can assemble packets that contain different data from different memory and have different structures in the end. How does it work? So basically, the architecture, it's mostly a traditional NIC in the sense that you have a DMA engine, right, to basically move the memory, and you have a packetizer to basically create the packets that will be transmitted on the wire. But you have a few new components. Most importantly, you have this optimizer here, right? We'll have a look at this in a second. And you have also a payload assembler, which basically is notified by the DMA engine once it has fetched some memory, and it assembles the different payloads to create the packets. Here is one look at the optimizer, right? So what does it do? Basically, you have some bounding boxes here, right? You want those regions without those holes. And then the optimizer will enumerate different versions of those bounding boxes, which could still lead to the engine transmitting those different grayed boxes here, but potentially in different ways and more effectively, right? So it calculates the bounding boxes alternatives, the different possibilities to fetch the data, and then it picks the best one, right? For example, if you have like 3 DMA reads, 2 DMA reads with 1 gap, or you can swallow the whole thing, right? So you have different ways of basically executing this through different DMAs and then a bit of filtering at the very end. And we did this in practice, right? We implement this in a smart NIC, and basically we got very good performance. We got from 18 gigabit per second per CPU core to basically 98, which is almost like a maximum of the line here, and 0 CPU usage, right? So you see that the advantage is double. By optimizing the transfer, you can get much higher throughput for those nitty-gritty, again, like complex data transfers of bytes and patterns, but also you save energy, you save CPU capacity, so you can use the CPU for more important tasks. And of course, you know, this can be expanded in many ways. So for example, we did not yet touch too much on more complex patterns, which could include, for example, bitmapped. You know, in a column store, typically, so you store your data in columns, and you have bitmaps for operations or for disabling some of the entries of your columns, right? So the bitmaps tell you something about each element in the column, right? You can use this for joins or again for to erase part of the data. So we are not exactly sure yet how to efficiently do DMA using a bitmap, but we have some ideas, right, how you could optimize this. And where have we been using this in SmartEdge? It's mostly, you know, as an accelerator to transmit and filter at the same time data, right? Typically, our use case initially was this license plate removal, right? You have some vehicle, it transmits some video frames, and you will basically select some holes in this image to remove some private data. Basically, could be the license plate again. Okay, so that's one kind of hardware acceleration we are excited about. So smart programmable switches, we are super excited about this. So when I say a switch, right, it can be you can call it a router or whatever you want, but basically those are those beasts which are extremely efficient these days at forwarding packets, right, to different outputs. Those switches are very different from what they were 20 years ago, and many of them today, they are programmable. Why are they programmable in the first place? Because, you know, the standards in terms of the transmissions, the networking stack, it changes, right? So before, you kind of had to really replace your equipment or at least upgrade the equipment for each new big change in your networking environment. That's why, you know, they started to introduce programmability in this and also to do some fancy networking, obviously. So what we are doing actually is exploiting this for data processing again, right? So the idea is, since those machines are so powerful, why don't you do a bit of processing using those primitives such that you can accelerate your whole workload, right? So that's a typical smart programmable switch. What do you have in this switch? You have a control plane where you kind of manage the data, and the data plane, which is really like pushing the data through different pipelines. And that's the internal architecture. You have some parser, deparser, you have some traffic managers, and you have those MAUs, right? Those match action units, which are actually the core of the engine, right? You will match some data with some action, and you have some memory as well, right? This is called match action table. So what is programmable? You can, of course, decide on the different fields you have in your packets, because all of this is based on packets, obviously, right? It's a switch, so you don't have files, you don't have what? You don't have loops, you just have packets, right? So you have different fields, and of course you can define how you pass those different fields. And then you have those tables, and you can decide on the table layouts. First of all, you can define the different actions you take and different types of matches you do, right? So you can define all of this. We worked on two main use cases using this smart routers. We worked on first SQL, right? We are database people, so we started with SQL. How can we do a bit of SQL with this? And then we worked on graph pattern mining, GPM. What is graph pattern mining? As most of you know, it's the basic primitives to analyze most of the graphs, right? So it's a very basic primitive where you kind of try to get subgraph in a big graph, and you try to match parts of those subgraphs using patterns, right? So you can have small patterns, like here, this wedge or a triangle. Very important to, for example, know in a graph how many triangles you have for all kinds of reasons. And you can have much more complex patterns, like, you know, here, this tail triangle, and bigger patterns, of course. So GPM is very generic. It encompasses clicks, motifs, also frequent subgraph mining. And it's used a lot, right? It's used a lot for queries, for data mining, for networking, for graph analysis, for bioinformatics, etc. So we thought it was a very powerful primitive to start working on. How does this work, this graph pattern mining algorithm? Usually, it works iteratively in terms of enumerating subgraphs. So what you do is you start with, let's say, this blue subgraph here in a big graph, and then you will extend node by node this subgraph and check on your constraints, right? So this is called first the subgraph enumeration. So if you have this graph, you start with this subgraph here, you can enumerate a bigger graph taking this edge here and having this new subgraph. Or for example, you can take this graph, this edge here, and having this subgraph, okay? So from a first subgraph, you get two more candidates, right? Two new subgraphs. And then you have to filter those candidates, meaning that you have to check whether those new candidates, they match the pattern you are interested or not. So if you are looking for triangles, right? You have to check whether this subgraph, there is an edge here and it matches a triangle, so this will be a positive match. Or if this guy here, basically, if you can create a triangle and you can't. Right? So this sounds easy, but guess what? Actually, that's why you have zillions of papers in this area. This is very hard in practice for a bunch of reasons. First, you have very complex data dependencies in a graph, right? I always say that for us computer scientists, we love graphs because they are exceedingly expressive, but usually they are the most complex data structures we have, right? Usually you can transform something into a graph without losing information, but the other way around is very difficult. In terms of GPM, one of the big issues is that the results increase dramatically as the size of the pattern grow. Right here you have basically the number of results which are generated in billions, and the pattern size, clicks, subgraphs. Obviously you have more subgraphs than clicks, but you can see that, you know, if you have few subgraphs for a pattern of 3, for 4 it will grow substantially, and 5 you will have suddenly, like, you know, 40 billion subgraphs generated. Right? And you have to check all of those to see which ones are relevant for your query. So this generates enormous amounts of results, but even more intermediary results. Right? So this is very expensive, both in terms of computation, but also in terms of memory. The other problem we have is that those real-world graphs are heavily skewed. So basically, you know, graphs, real-world graphs, they are very often exponential in terms of their degree distribution. They are small world, they have all kinds of properties. And it means that, you know, a few highly connected nodes are responsible for many of the work we do, right? For much of the work. So basically, a few nodes generate a substantial amount of those different subgraphs here. And this is true for all natural graphs, right? Like the web, or, you know, a query, or humans, or, you know, microbes. This is very bad for us in a distributed setting, because as you know, when you have skew, you don't know how to distribute the work to the different workers, right? So you have irregular workloads across the workers. And hence, it's very difficult to do this at scale to achieve high utilization and scalability. And that's how, you know, a typical GPM system works. You have servers, and you exchange those different candidates through the network. And of course, the network is passive, and all the work happens on the servers. So what we did, now you understand the idea, right? That's a paper we published at SIGMOD last year, was it? Or 2 years ago? Last year, I guess. We did Graph Inc. So it's basically this graph pattern mining, but using this hardware accelerated switch, high-speed switch, which can do a lot, right? It can deliver billions of packets per second at line rate. And the idea is that, you know, the server do part of the work, but actually the network will be quote-unquote smart. The network will actually do not only like forward packets, but do processing directly while it forwards packets to the different servers. This sounds fantastic, right? The student who worked on this, Hannah, was fantastic, but it took her a lot of time to program all of this, because the network has limited storage. Also, it has a very limited programming model, different variations of P4. And I guess many of you know P4. P4 is a low-level language. It depends on the versions, but it's in between like C and some flavor of C++. It's very limited in the sense that, as you understand, the switch doesn't have like an SSD to store data, right? So everything has to go at line speed. You cannot basically slow down, do some complex operation of the switch. Otherwise, the switch will not be able to take some input and do the output, right? So you don't have any choice in this model. It has to work at line speed. So it has to, you know, the switch has to do all the operations in those MAU in one forward pass. Otherwise, it will not compile. How do we split the work between the servers and the switch? So we can have many servers typically and one or several switch, but few switches, right? What the state of the art does is obviously distribute this big kind of spike in terms of, you know, the generated clicks, or this is like the nodes and the generated clicks. So you see that there is this big skew, right? As I said, few nodes are responsible for many of the work we do. So instead of trying to splitting this, which is very condensed and hence very difficult, we have a radical approach. We concentrate all the skew to the switch. So we take all the hard part and give it to the switch. Why? Again, because the switch is much more powerful than a powerful server at doing this, if we can do this in a feed-forward, like line speed manner. Right? And basically, we have this, kind of best effort approach to split this such that it's very good in terms of the performance. Typically, we take a very small part of the graph on the switch, but which generates like half of the results, right? So it's funny, you take very little memory in the end, and we have little memory on the switch, but this is enough, this very little memory, like, you know, 0.1% of the nodes, to be able to treat half of the workload directly on the switch. So how does it work? What you have to do if you want to take advantage of those super powerful switch is think like a packet. You know, you have to retrofit your algorithm as a kind of packet forwarding, right? Because the only thing it knows, again, is packet, lookup, change the packet, and forward the packet. So we have those MAUs with 2 different stages. As you remember, we enumerate the subgraphs node by node. We grow the subgraphs, and then we filter the subgraphs to see if the subgraphs, they match the pattern you are interested in. So let's imagine you have a packet coming in, and guess what you have in a packet? You have subgraphs, right? So here you have a packet. With this small subgraph here, you have 2 nodes which are connected. Then what you will do first is look at the neighborhood of nodes to get a new bigger subgraph, and here you will extend this subgraph because with these 2, because you know that 1 is connected to 2, right? So you generate here in this MAU using those registers of neighborhoods of nodes. You enumerate a new candidate, and then you pass this candidate to the next phase, and you will check if this candidate is a good candidate. Let's imagine you try to find triangles. You will look up at a different table asking, oh, for this to be a triangle, I need an edge between those 2 nodes. Is there an edge between those 2 nodes? Yes, action edge found. Edge found, you found a new subgraph, and then you will do this at line rate. So we do this at 400 gigabit per second, right? Using different pipelines. So this is very, very powerful. And then potentially what you can do is forward this further, or you can recirculate this up, and then you have this new subgraph as a new input. So how does this work in terms of performance? We tested this on several, well-known graphs, some small, some large, some very dense and skewed, some less skewed. And you divide the load between some servers and the switch. And again, I want to say that the switch, okay, it's a powerful switch, but in many of the environments you work with, you have such powerful switch, right? They are getting the norm. And so basically we have, I would argue, 50x performance gains on average. So we have more than 1 order of magnitude speed up. Why? Because again, we could retrofit this kind of complex task for the servers, dividing this big complex skew of the graph. We can retrofit this into fast forward algorithms on the switch, which is very powerful for those kinds of operations. And obviously it's kind of fun to do experiments in this setup, because you have here in blue you have the servers, in orange you have the switch, and you can have a trade-off if you want to use the servers more, or if you want to use the switch more, and that's what we did in terms of our algorithm, if you want to have some kind of a trade-off between the 2, such that basically the latency is minimized, right? So if you want to minimize latency, you should optimize your assignments such that they are both more or less at the same processing at the same duration of time. And what are we doing now in terms of extension? We are trying to extend this to Sparkle. I think it's a great opportunity for SmartEdge because, as you know, every node should have some P4 capability in SmartEdge. So we are working with Dan and Theo Berlin to try to do this. So we had in the past, Fribourg did some hardware-accelerated SQL and graph processing. And as you know, Sparkle is a bit in between, right? Sparkle, it's a bit of SQL and it's a bit of graphs. So we hope that we can support a subset of Sparkle. We still have to discuss, obviously, the details. Okay, last part I want to touch on is what Eduardo did recently. It's similar, but on a bigger picture for SmartEdge. It's some kind of an optimizer to basically optimize some more complex workloads on P4 node. And hopefully we can use, this Sparkle thingy on different nodes and then optimize this using the optimizer. So again, it's a very DB-centric approach if you know a bit how data-intensive systems work. So you have this, typical edge computing architecture. You have perhaps some cloud nodes, which are very powerful but far from the edge. You have switch between like the cloud and edge nodes, and again, some switch potentially between the edge nodes and edge devices. And you have this whole continuum, right, of mobile edge devices which don't have much connectivity and limited power, and then perhaps edge nodes which have a bit more through a switch, and then the cloud which is more powerful. So the question is, how can you basically optimize some complex workloads in this? We take a DB approach by having an optimizer which takes some queries, and you can have many of such queries. You can have small queries, bigger queries, queries which are distributed, obviously, if you want to use different edge devices together, right? Typically what you do is you create some kind of a tree, right, or a DAG to have all the different operations you want, and they are connected by, in a sequence through edges. We build an intermediate representation for all of this, and then we basically try to split P4 pipelines to execute those queries in a hardware accelerated way. But also you have some optimizer. What does the optimizer do? It has some optimizations in a system catalog, and then it will rewrite basically those P4 pipelines to have more efficient pipelines, right? If you have many nodes doing the same thing, it will try to perhaps combine the nodes. If it has sequences of nodes which can be combined, it will combine those nodes. There are lots of tricks we can play. So here are some tricks that Eduardo defined. The first is simply memory allocation on those, P4 or switch devices. This is actually very difficult, much more difficult than it sounds. The documentation gives you some option, but actually what you can do with the hardware is different, right? You have basically two pipelines, the ingress and the egress, and you have those blocks you can allocate. So the first thing we did is, given some pipelines, allocate automatically all the different stages, right? So you can allocate those different blocks you want to operate on in one stage, but also in several stages. And you can use parallelism to do this in different pipelines as well. And then I will not go into the details, but this is a bit of, query optimization in terms of logical plan or physical plan. We did a bunch of optimizations. For example, reshaping the plan. It's very funny because some of the operations, obviously, you do on the switch are very efficient given how the switch works, and they are not efficient at all on a server, right? So basically, the way you optimize the queries on the switch is very different from what you do in Microsoft SQL Server or Postgres, right? Typically, we love those write-deep query plans, which are usually a nightmare in many database systems. But, since you can do some streaming and some building on the fly using the switch, this is actually very efficient. You can also fuse operations, right? Sometimes you have enough memory and tables on the switch such that if you have, like, here those two joints, you can fuse them in one segment and do them all at once on the switch. You can also merge different segments, right? Here you have two redistributes basically, and you can merge all of them into kind of a drain using a multi-join. So this is not yet published. We will try to publish this in the coming months. I hope I can give you some more details and results in a few weeks. So let me now very quickly talk about the current focus we have. For SmartEdge, we are doing two things. First, we are trying to optimize a bit further all of those transmission between devices, between nodes, right? And for this, we are very excited to use CXL. I might have already told you a bit about CXL. CXL is the next big thing in terms of, architecture and memory expanders. So what is it? It's a big new standard, which is not super ready yet, but it's still being used by companies, by Intel, by many startups, by us. So what does it allow you to do, CXL? It allows you to expand a host with a peripheral, right? So this is great for all our hardware accelerated things because you can see this as expanders, right, with their own memory. And the host and the device can update the memory, and then the memory is coherent, right? So you don't need to do it manually. You can basically use this new CXL hardware to do memory coherence across the different regions in your host. And what we started to do are what we call kernels. It basically means that you have specific memory kind of banks or parts of the memory which have specific semantics in terms of what they do. So basically we have specific parts of the memory which can directly compute some stuff, if you wish, or at least do some specific semantics in terms of your application, right? So 3 examples. If you're writing to a specific part of the memory, then you can do a low latency data pass and transmit this piece of memory further. For example, you can do logging, right? If you read from some area, you can have a computation directly on the read, and you can get some results directly from this computation. And for example, you can do read-write, decompress or compress the contents along the way. Like this, right? You would do compression, decompression without any CPU involvement and without having to basically tell the machines to do anything, right? It would be directly on the device itself. And we have a first paper about this, which was published this year at CIDR, if you're interested. And one example, just to give you an illustration of what you could do, and that's something we did actually a bit earlier, is to have, direct computation on an SSD, right? I told you about like switches, about NICs. Obviously, you can play similar tricks with disks, right? Because shuffling the data, transmitting the data from disk through a complex interface, which is, by the way, very bad in terms of the interface, how it was built, through some wires, through the memory hierarchy to go into the CPU is a huge waste of time. So if you can do some of the computation early on, right, you push down the computation to the SSD, you have a 100x, 1000x improvement. Right? So this was an experiment we did a couple of years ago. It's called Cross-SSD. It's an SSD which does automatically at a low level some of the operations, right? So what does it do? It has different sides, like different regions in this SSD. One side is accepting byte addressable requests at low latency, right? And one conventional side offering an SSD block interface. And depending where you kind of read or write in this SSD, it will then automatically log your operations, right, in a kind of a database log, right, to understand basically for recovery, right? If you have an issue, you will be able to recover the database. You can also, and we are very excited about this, replicate automatically the data. Because typically in a distributed system, if you do one operation, you want to replicate this to a different node. If there is some failure, you want to have a safe failover node that can take the replicated data. And all of this can be done at a very high throughput, low level automatically by this SSD. The second focus we had, I told you that Kari visited us last week, so we are working on LiDARs and point cloud hardware accelerated processing. And I cannot tell you too much about this now because we are really preparing the paper. But the idea is, you have some policies, right? You want to implement in terms of, for example, traffic. You have some potentially LiDAR, several of them, and you want to basically pre-process the LiDAR data using some hardware acceleration to be able to enable your city policy, right? So we define this at again, like high-level declarative interface. We have this point cloud manipulation language that we are defining, and where basically, we'll have some FPGA directly on board at the edge doing most of the processing for the LiDAR. And this is again ongoing right now using this PCML language and low-code programmability. Okay, that's all I wanted to tell you today. I hope you understand a bit the idea, right? It's leveraging all kinds of weird devices and weird optimization, but to gain not 10%, right? So this is very, I would argue, hard what we're doing, because this is low level. Again, the students kind of suffer a bit sometimes, because some of you know it, right? If you want to do some efficient P4, it's very tricky. But at the same time, if you do it correctly, again, you gain 1,000%, right? It's not like you're gaining 20% out of this. So we are super excited about this, and we are super excited about the next steps in terms of this hardware acceleration for SmartEdge. Thanks a lot.